Welcome to the deep dive. We've got quite a bit of material here, all centered on one specific thing, polyurethane foam insulation.
Yeah, you hear all different things, right?
Mm.
Spray foam, SPF, sometimes even puff insulation.
Exactly. And today, we're really digging into these sources to understand what this stuff actually is.
What's the chemistry behind it? How does it perform? According to what we're seeing here, what are the benefits, the reasons people go for it?
And, crucially, what are the downsides? What do you really need to be aware of?
It's fascinating stuff. The sources talk about how it starts as a liquid, then just poof.
Yeah, this huge expansion right on site offers, really high performance and can even make the building itself stronger.
But that whole transformation means it's definitely not your average weekend DIY project.
Not at all. So let's start right at the beginning. What is this foam actually, chemically speaking? Those sources get pretty technical.
They do. Okay, so fundamentally, it's described as a thermosetting polymer.
A type of plastic,
Yeah.
basically, but one that forms during installation.
Precisely. It's created by a chemical reaction when two main liquid components are mixed, literally seconds before they're sprayed.
Okay, component A and component B.
Right. Component A, that's usually an isocyanate, think MDI or TDI. The sources often call this the reactant. It's the key that kicks off the whole polymer building process.
And component B, the polyol resin.
Yeah, and that's not just one thing. It's actually a blend. It's got the polyols, which are like the main building partners for the isocyanate.
The other key part of the structure.
Exactly. But component B also contains catalysts, things like amines or tin compounds. Their job is just to make that reaction happen fast,
Speed it way up.
dramatically. And then, critically, you've got the blowing agents in there, too.
The blowing agents. That's what makes it foam up, right?
Yeah.
Turns the liquid mix into, well, foam.
That's the key. They create tiny gas bubbles that inflate the mixture as it reacts and hardens. The sources mention different ones: water, HFCs, hydrocarbons.
So for open cell foam, they often use water.
Yeah, and the water actually reacts chemically to produce carbon dioxide, K-Euro, and that gas is what expands the foam.
Wow. So the expansion isn't just air, it's gas being generated right inside the material itself.
It's a really rapid, controlled chemical event. And component B might have other things too, according to the sources. Surfactants to help the bubbles form nice and evenly.
Keep the structure consistent.
Right. Pigments, maybe UV stabilizers if it's going to see sunlight, and importantly, flame retardants.
Yeah, I was wondering about fire. Flame retardants seem essential for anything going into a building.
Oh, absolutely. The sources are very clear. These are added to meet fire safety standards and building codes like the ASTM E84 test for how materials burn.
Okay, so it's this reactive two-part liquid system, foams up using these blowing agents, and has other additives. But the sources also talk about different types of foam.
That's a really important distinction they make. Depending mostly on that polyol blend and the blowing agent, you end up with two main categories: open cell and closed cell foam. They behave quite differently.
Okay, let's unpack open cell first. What's that like?
Open cell, it's softer, kind of spongy to the touch. The name gives it away. The tiny cells or bubbles inside are interconnected like a sponge.
Lighter weight too?
Yeah, relatively low density. Sources say around 0.5 to maybe 0.7 pounds per cubic foot.
And often uses water as the blowing agent, making kudos.
Correct. Now, because those cells are open and mainly filled with air, it's R value. Its resistance to heat flow. It's good, but lower than the other type, typically around R3.5 to R4.5 per inch.
But it has another key feature.
Yes, that spongy structure the sources highlight makes it pretty good at absorbing sound, so useful if noise reduction is a big goal.
Okay, open cell. Softer, lighter, lower R value, good for sound. What about closed cell? Sounds like the opposite.
Pretty much. Closed cell foam is much more rigid, hard even, and the cells are sealed off from each other, completely separate bubbles.
And filled with something other than air.
Often, yes. They're filled with a special gas, a blowing agent like an HFC or hydrocarbon, think HFC 245 burfay or pentane. These gases are much better insulators than plain air.
And that makes it denser.
Oh yeah, significantly. Density jumps up to around 1.7 to 2.0 pounds per cubic foot. And because of those sealed cells filled with insulating gas, the R value is much higher.
How much higher?
The source is typically, quote, R6.0 to R7.0 per inch, sometimes even a bit more.
Wow, that's a big difference per inch.
Yeah.
So, okay, knowing there are these two types, what does that mean practically, beyond just the R value? Especially for closed cell.
Well, that rigid, sealed cell structure gives closed cells some really important properties the sources emphasize. First, because the cells are closed, it acts as a very effective barrier against air movement.
Air sealing.
Exactly. But also critically against moisture movement. It's a vapor barrier. This is a huge deal in preventing condensation inside walls, reducing mold risk, stopping drafts.
Improving indoor air quality. And didn't you mention something about strength earlier? The sources talk about structure.
Yes, that's one of the most striking things. Because it's rigid and bonds so tightly, closed cell foam can actually add significant structural reinforcement to walls and roofs.
How much?
The sources cite figures saying it can potentially increase the racking strength, the rigidity, by up to 300%. It's a pretty substantial structural bonus.
Okay, so if you're looking at this material, how do you decide between open and closed cell? What's the trade-off for you?
It really comes down to the specific job, you know?
Yeah?
Where in the building is it going? What's the priority?
Like soundproofing.
Yeah, if soundproofing is the main goal and you don't need a super high R value per inch or a built-in vapor barrier, open cell could be a good fit. It's also generally a bit cheaper per installed R value.
But if you need maximum insulation in a thin space,
Then closed cell is the way to go. Or if you absolutely need that moisture barrier, like in a basement or crawl space, or if you value that extra structural rigidity, closed cell is usually the better choice. The sources make these trade-offs pretty clear.
right? And installing this, it's not like fiberglass baths you just unroll. The process sounds really specific.
Oh, absolutely. It's a specialized process. The sources detail several key steps, starting with prep work.
Getting the surface ready.
Exactly. Whatever you're spraying onto wood studs, concrete, metal decking, it has to be clean, dry, and totally free of dust, grease, anything that might interfere with the bond.
Temperature matters too.
Yes, the sources mention ideal temperature ranges, often somewhere between 50 and 90 degrees Fahrenheit, for both the surface and the air, so the chemicals react properly.
Then the spray rig comes in.
That's right. This is where the specialized gear is essential. You have these big drums or tanks of component A and component B. They get pumped into the spray foam rig.
Which heats them up.
Yep, heats them, often through heated hoses, and pumps them under high pressure to the spray gun where they're mixed, usually at a very precise 1-to-1 ratio right at the nozzle.
And boom, the reaction starts immediately.
Instantly. The technician sprays the mixed liquid onto the surface, and within seconds, it starts expanding dramatically.
How much expansion are we talking?
The sources say anywhere from 30 to, 100 times its original liquid volume. It just foams up incredibly fast, filling every nook and cranny, sealing gaps as it goes.
Wow, 30 to 100 times.
Yeah,
It's hard to even picture that happening inside your wall cavity.
it's quite something to see. Then, after it expands, it needs time to cure, to fully harden. The sources say this can take, maybe 24 to 72 hours, depending on the foam type, humidity, temperature.
And sometimes it needs trimming.
Yeah, if it expands out past the framing members, they'll trim it flush so you can install drywall or whatever comes next.
Okay, this whole process, I can definitely see why the sources keep stressing the need for trained professionals.
Absolutely.
So, given all this chemistry, the specialized application, why do people choose PUF? What are the big advantages the sources point to?
Well, it really boils down to performance benefits that are hard to beat with older methods.
Top of the list has to be thermal performance, right? The R value.
Yeah, number one, especially closed cell with R values up to 7 per inch. That significantly cuts down heat loss or gain. The sources often cite potential energy savings, maybe 30 to 50% reductions in heating and cooling costs compared to, say, poorly installed fiberglass.
Well, it's not just the R value, it's the air sealing too.
That's arguably just as important, maybe more so, because it's sprayed as a liquid that expands. It creates this seamless, continuous barrier. It seals all those tiny cracks and gaps where air leaks occur. Bad insulation just can't do that nearly as well on its own.
And that air sealing must make a huge difference in comfort, drafts.
Totally. And we talked about the moisture barrier aspect of closed cell too. Preventing moisture movement through the wall assembly is key for durability, preventing mold. Big benefits there.
Plus that structural reinforcement you mentioned for closed cell.
Right, that potential 300% increase in racking strength. That's a significant bonus, the sources highlight, especially maybe in high wind areas or for adding stiffness to older buildings.
How long does this stuff last?
Longevity is another plus. Unlike some materials that might settle or sag over decades, creating gaps, PUF holds its shape. The sources suggest it can last for the life of the building, potentially 80 years or more, without degrading significantly.
And we shouldn't forget the sound dampening, especially for open cell.
True. If acoustic control is a priority, the sources point to open cell being quite effective there.
The sources also mention some evolution on the environmental side, with the blowing agents.
Yes, they do note that. The industry has moved away from older blowing agents like CFCs and HCFCs, which were bad for the ozone layer and had high global warming potential.
So what's used now?
Modern foams use HFCs, and increasingly a newer generation called HFOs, hydrofluorolefins. The sources present these HFOs as having a much, much lower global warming potential, GWP, compared to the HFCs. So there's definitely been progress there.
An effort to reduce the environmental footprint.
Exactly. Though it's important to remember these are still manufactured chemicals that need proper handling and fall under environmental regulations.
Okay, so lots of potential benefits. But like anything, there have to be downsides or things to watch out for. What do the sources say about limitations or safety concerns?
Safety during installation is a big one. The sources are very clear. While the foam is being sprayed and before it fully cures, it releases VOCs, volatile organic compounds.
Fumes, basically.
Yes, and isocyanates themselves require careful handling. That's why professional installers absolutely must wear full personal protective equipment respirators with specific filters, gloves, eye protection, full suits. The area needs to be well ventilated, and occupants usually need to stay out during and shortly after application.
And the fire aspect, we mentioned flame retardants.
Right, it's worth repeating. The foam itself is combustible. The flame retardants are added specifically so the finished product meets building code fire safety requirements. Understanding that it relies on these additives is key.
And environmentally, even the newer blowing agents, while better, are still chemicals under scrutiny.
Correct. The sources acknowledge the improvement with HFOs, but frame it as part of the ongoing discussion about the life cycle impact of building materials.
What about other limitations? Cost seems like a big one.
Definitely. The sources consistently point out that PUF is significantly more expensive upfront than traditional options like fiberglass or cellulose,
How much more?
often quoted as 2 to 3 times the installed cost. The sources give ranges like maybe $1.53 to $3.50 per board foot. That's a measure of volume 1 foot by 1 foot by 1 inch thick.
That's a substantial difference.
It really is. And tied into that cost is the need for professional installation. While you might see small DIY kits for ceiling gaps, the sources strongly emphasize that for insulating whole walls or attics, achieving the proper performance and safety requires trained technicians with that specialized, expensive equipment.
The mixing, the reaction speed, it's complex.
Very. You need precision. And the sources also mention a potential risk if it's not done right, overspraying. If too much foam expands too quickly in a tight, enclosed space, it can actually exert pressure.
Enough to damage something.
Potentially, yeah. It could bow drywall, maybe even distort window frames if not applied carefully and in controlled layers or lifts. It just reinforces why expertise matters so much here.
Okay, so weighing the high performance against the higher cost and the need for pros, where do the sources say we typically see PUF being used?
It's pretty versatile, according to the sources. Very common in residential construction attics, rim joists in basements, walls, especially where achieving a good air seal is critical.
Commercial buildings, too.
Yep. Insulating HVAC ducts, cold storage facilities, warehouses, anywhere. Thermal control and preventing condensation is really important. And even in industrial settings, like insulating pipelines or tanks, refrigeration units.
So wrapping this up, our deep dive into these sources shows polyurethane foam insulation as, well, a really high-performance option.
Yeah.
Great thermal resistance, excellent air sealing, moisture control.
And that added structural kick from closed cell. It's definitely presented as a product of some pretty advanced chemistry delivering real-world benefits.
But, as the sources make equally clear, it comes with that higher price tag and the absolute necessity of professional, careful installation due to the chemicals and the process itself.
Yeah, the takeaway seems to be understand the difference between open and closed cell, know why you're choosing it for a specific application, and definitely work with certified installers who know the codes and safety procedures inside out.
That seems to be the consistent message. Understanding the details really empowers you if you're considering this for, say, a renovation or a new build.
Absolutely.
Thinking about this balance, the really top-tier performance PUF offers versus the significant upfront investment and the specialized handling it requires. It really makes you wonder, what factors are becoming most critical when people make decisions about buildings today? Is it purely about long-term energy savings, upfront cost, structural integrity, or the environmental profile across the whole life cycle? It's a complex calculation.
Please do subscribe.